Hello, and welcome to episode number 20 of CS350 Online. I'm your host, as always, Leslie, and in today's episode, we're going to conclude our discussion of devices and I/O, and then in our next episode, we'll be moving on to the big topic of file systems. But first, of course, the OS of the day. So finally, we have reached a point in time where we can actually discuss Mac OS. So that's maybe kind of exciting for some of you. Mac OS, of course, is a product of Apple, and it was released in 1984. And in fact, one of the little clips that we had was actually one of the Apple release commercials for this. Just kind of a fun little commercial pawned off of the book 1984. Now, as I've mentioned before, the desktop environment of Mac OS was actually really inspired by the Xerox Alto operating system, Alto Executive, because Steve Jobs had actually visited them to get that experience and learn about it. But if you were to look at Mac OS's history, you could actually subdivide it into two major variants of the operating system. And actually, the funny story is you can do the same thing with Windows, and we'll talk about Windows another day. So there's the classic era of Mac OS, and that might predate you a little bit. That kind of disappeared right around 1999, 2000, 2001. That's when you start to see us move away from the classic version. But the classic version, what's really interesting about it was they really wanted to make sure that you had a well-performing piece of hardware and that the user interactions actually happen in a reasonable time frame. So what's interesting about it was that they actually partially stored the operating system on a ROM chip. Now, for those of you who aren't familiar with what that stands for, it means read-only memory chip. So essentially, you actually have part of the operating system is being stored in hardware. And that means that it's going to be much faster to load because you're not going to have to go to a slower form of secondary storage. And in 1984, in the 80s, and the 90s, believe me, secondary storage was incredibly slow, at least by today's standards. Now, another interesting thing is that they had a flat file system, so the concept of having like a hierarchy wasn't exactly a thing. And some other interesting notes is they didn't actually support multi-processes until about 1987. And even then, I want to say it wasn't supported in the way that you might anticipate. So keep in mind, at this point in time, you've got things like OpenVMS, and you've got Unix, and you've got Multics, and you've got all these other operating systems that are doing full multi-process, multi-CPU, multi-threading with preemptive concurrency, and they've been in operation for a really long time. But Mac OS, Apple, they decided that they wouldn't even support cooperative multitasking completely until 1991. Now, if you remember, cooperative concurrency means that there's no preemption actually happening. And then in order for a context switch to happen, it has to be because a thread yields, or it's because a thread terminates, or because a thread blocks. And so that's why we call it cooperative, because if you actually want threads to actually have a context switch, they actually have to do it on purpose. And this, you're looking at 1991 and you might be thinking to yourself, this is a big deal that Apple didn't provide preemptive concurrency in 91. But, I want to challenge that notion because, so I had used an Apple computer back in those early days, and I had used computers back in the late 80s and the early 90s. The concept or the idea that you could actually run two programs at the same time for the average user just didn't exist. Now, I'm sure there were power users and business individuals who would have found that particularly useful, but I want to say the average home user, the thought that you could actually run WordPerfect at the same time as your video game like Zaxxon, that just didn't cross your mind. And in 91, we certainly weren't thinking about the internet. I didn't actually start using the internet. I feel like it was right around 95, 96. So even the thought of having multiple web browsers open wasn't really a thing. So that survived. And another interesting thing about the Classic Edition is that they didn't even get virtual memory until 1991. Which again, that kind of makes sense because if you're not really supporting any kind of threading, then it doesn't really matter almost. Now, obviously, this classic version of Mac OS didn't last forever. And eventually Apple realized that they were going down a road that didn't make sense moving forward into the future. So they needed to make a new operating system that actually had a new kernel that was able to support the modern ideas that every other commercial operating system had. So they wanted it to have preemptive concurrency, virtual memory, which they sort of had already, protection, and all of those lovely things that we've come to know and love in operating systems. And so instead of developing their own operating system from scratch, they actually acquired a company called Next Step, which had their own version of BSD. And they've made their modifications to that and turned it into Mac OS X. And that came out in about 2001. So Mac OS X, as you have it sitting in front of you now, which I'm going to guess is probably at least 30 to 40% if you have an Apple computer, you're using a variant of BSD. And I mean, if you didn't know it was a Unix-like operating system, there are many ways that you could actually tell, because you can open a terminal and you can actually type things like ls. All of those old tools, all those old little programs and pipes and all of those things, they're there. So if that didn't clue you into this as a Unix-like operating system, hopefully that does. Now, one of the big things is, instead of inheriting some of the Unix-based file systems or the BSD file systems, Apple kind of kept its own file system. Now, up until the release of High Sierra, Apple was actually using HFS and HFS Plus, which is unfortunately a case-insensitive file system, which means that you could have a file named, oh my gosh, I'm late for my assignment submission, all uppercase, and that was equivalent to every other file with every other combination of upper and lowercase letters, of course with the same actual words. So, and I mean, Apple had been criticized by that by numerous people, and so with the release of High Sierra, they decided that they were actually going to release a new file system. Now, the new file system that they released, I believe, is called APFS, and it wasn't for every computer. So HFS and HFS Plus, they haven't actually disappeared. They're still in use, but they're meant to be used on mechanical hard drives, so the hard drives that we've been talking about in class, whereas APFS has been optimized for SSDs, which is in their laptops and all of their portable computers. So APFS, if you have High Sierra or Catalina, that's what you're using. And it is case sensitive. And one of the interesting things is, if you made the switch from, I think it was like Mojave, I don't even remember, to High Sierra, and you just kind of did it blindly, it was entirely possible that a good number of your programs actually stopped working because they were operating under the principle that the case of the file name didn't matter. So things like old Photoshop CS5 actually had a problem when I upgraded to High Sierra, which is actually why I no longer have Photoshop. And I've been using the GIMP because I don't want to pay for a Photoshop license right now. All right. Now, one of the other interesting things about Apple's operating systems is, if we were to talk about the look and feel, Apple's been quite consistent in the look and feel of their operating system. And I can't really say that for any other OS. So if we actually look at, this is Apple One, Mac OS One. And yes, it's in black and white and dithered graphics, but I want to say that what you're looking at is very similar to what you have now. You've still got the Apple in the upper corner and the menu bar across the top. You've got your minimize and whatever buttons in the upper left corner and things like that. Now, you're missing the dock from down below, but that does, this is version 1. They're going to make improvements, but they keep that consistent look and feel. And then if we look at, this is the last of the classic editions. You've got the presence of the dock kind of showing up in the bottom. Kind of funny story. This does kind of look like OS2 Warp. And then you've still got the menu stuff up at the top. And I mean, you know what modern Mac OS X looks like because most of you have it or have seen it before, so I won't show you that. But when we actually look at Windows, what you'll see is that it's almost like every couple versions of Windows, it gets a completely new look and feel. which is kind of interesting when you compare the two. One of them has a consistent look and feel, and the other one just doesn't. All right, that was a long rant about Apple. All right, so where I wanted to go to next is talking about where we left off. So we were talking about, because I know it was a few days ago, we were actually talking about disks. And in particular, we were looking at these mechanical drives, and we had noted that because there are actual physical moving parts, that to do any kind of I/O operation that's a read or write, it was actually going to take a lot of time. And so we looked at the costs associated with that. So we saw that the seek time is the amount of time it takes to remove the read-write head to the correct track. And if you don't remember the term track, that's the concentric rings on your platters. And then the rotational latency is the time it takes for the correct sector to fall underneath the read-write head. Now, some people say, why don't you do seek and rotational latency at the same time and then pause the motion of the disk? But the problem is the disk, because it takes so long to spin up and spin down, what we actually do is the platter never stops spinning. So as you're moving the read-write head to the correct track, the platter is actually still spinning. And what's interesting is that the correct sector may actually come under the head several times as it's going into place. So rotational latency, we're always going to have that. The minimum is by chance you are at, of course, the right sector when the read-write head is in the right position. And the maximum, of course, is that you have to do a complete rotation of the disk. Then the transfer time is the actual time it takes to rotate the platters through the sectors that you actually wanted to read. So it's going to represent a fraction of the time it takes to read one of the tracks of the disk. And then to compute the request service time, we sum up these three costs, and that's how long it takes us to actually do an I/O operation. And for those of you that don't remember, there are a bunch of formulas on slide 16. And if you go onto Piazza, there is also, let's put Piazza here. Let's open up Piazza. Hit the escape button and actually have it work. That would be so nice. There we go. So let's bring up, oh, I love it when Chrome crashes. Don't you? It's not crashed, it's just being slow. And it's probably because I have so many tabs open. Does this to me all the time. I want to show you this on Piazza, though, because I really want to make sure that you are aware of all of the resources that you actually have available to you to complete the course. Application not responding. And there go my fans. That's so much fun. Oh, has it crashed everything? Yep. You can't even force quit out at this point. Well, let's start it back up again. Let's see what happens. Let's restore everything. See, the problem is once I restore everything, it's going to be like, I don't like this anymore. Where's Piazza? There's Piazza. Okay. Now it's going to load back up. So if you go into the pinned posts and you go to extra sample problems and lecture content, what you'll see here is a disk guide, disk drive math. And that PDF is going to have all of the formulas again, and it's going to have examples of how to use each of them. So if you're struggling to understand the disk drive math, this is a guide that you're going to want to use. And if you're sitting there wondering when it comes to quizzes or the final assessment, am I allowed to have these guides open? The quizzes and the final assessment are open book because I'm not going to use some kind of online proctoring software because that is not only like asking you to install a rootkit on your computer, but that's also a huge invasion of your privacy and it's just wrong. Anyways, so there's the disk guide here for you to take a look at. Now, we ended last class talking about how because the Seeks were so expensive, we wanted to actually try to reduce the amount of time that we were doing seek. And we made the observation that if you had really long sequential IO operations, that you'd be minimizing the seek time overall because you wouldn't have to move the read-write head to different tracks very often. However, unfortunately, sequential IO is not generally what's happening on your computer. It's actually more like random IO because your file isn't usually stored in just one sequential place on your disk. It's actually usually scattered to the wind. So what we do is we actually do this concept of disk head scheduling. Since there are so many jobs to actually perform with your disk, we're going to end up with like a queue of jobs, and then we're going to schedule those jobs in such a way that we are minimizing, or hopefully minimizing, the amount of travel that the read-write head actually has to go on. So for example, we could do first come, first served, which we talked about, or we could do something like shortest seek time first, which is very much like shortest job first, but unfortunately, like shortest job first, it also has starvation problems. And then we looked at the elevator algorithm, which is we are going to pick a direction, we are going to travel in that direction until we get to the end, and then we are going to turn around and come back. Okay. So at the very end of class, I offered you a sample problem to try. So let's actually open that sample problem up. Now I'm going to assume that everyone forgot that I had given you a sample problem. And again, this sample problem is also posted on Piazza. So there's two parts. Let's take a look at it now. So we have a server and it has access to a single disk drive and a single core processor. And there are K processes running in the system, and each process is the same thing. So it does the same thing. And that is, it's going to do 5 milliseconds of run, like just regular computation, followed by requesting a 4 kilobyte block of data from the disk. And it's going to do that ad infinitum. So we're going to do 5 milliseconds of compute, IO operation, 5 milliseconds of compute, read operation. Now, because we're doing a read operation, we know that that process is actually going to have to wait in order to do its next compute cycle because it's going to need the results of reading from the disk. Okay. So we've described the disk here as having, 1,024 tracks and a total capacity of 128 megabytes. So this is like 1992. And according to the manufacturer, the disk's average seek time is 5 milliseconds, and the disk spins at 100 rotations per second. So the first question is asking, if there's only one process in the system, what is the CPU's utilization? Now that's something we haven't actually talked about, is the utilization of the CPU. But what does that mean? Well, what the CPU utilization means is for a unit of time, what percentage is the CPU actually doing computation, and what percentage of the time is the CPU doing some kind, like idle in some way. So we're going to open OneNote back up and hope it behaves. Of course, it doesn't like to behave, but there we go. Right. And I had my pen on this morning, but the problem is my son likes to come along and he likes to push the button on my pen. And so my pen falls asleep and then it doesn't want to connect again. And I'm connecting by Bluetooth, so of course it's kind of buggy. All right. So let's just talk about this problem to start with. So the first thing that we need to do is we actually need to figure out how long does it actually take to do the IO operation? Because I can't determine the utilization of the CPU if I don't know how long the IO operation is going to take. And remember, this matters because we are reading from the disk, because we need that data. So while we are reading from the disk, because we, process 1, are waiting for the data, we are going to block, which means that the CPU would actually be idle during that time. So let's actually do that computation. So let's figure out our disk here. Sometimes I really despise Bluetooth devices. Maybe I can force the issue here. Oh, there we go. So, what have we got? So, we first need to know the seek time. Well, we don't know what track we are on, and we don't know what track we are going to. So we're going to use the average seek time. Now, luckily, the average seek time was actually provided to us by the question. So the average seek time is 5 milliseconds. Next, we need to know the rotational latency. Now, again, we do not know what sector the disk is going to be on when the read-write head is in the right position, and we don't know where it needs to go to. So we're going to use the average rotational latency. But unfortunately, all we have is how many rotations per second it makes. So to do the rotations, we need to figure out if it does 100 rotations per second, how long does it take to do a single rotation? And the math formula for this, of course, I'll let you figure that one out. But let's just say a full rotation is 10 milliseconds. Because we do 100 per second. Okay? Now, we don't want to know the speed of a full rotation for this particular, for the rotational latency. We need the average rotational latency. And remember, we're going to just take this and divide it by 2. So the average rotational latency is going to be 10 milliseconds over 2, which is going to give us 5 milliseconds. Okay. It's not too bad. Now, the next question that we have is the transfer time. Now, to compute the transfer time, we actually need to figure out what portion of a track are we actually reading? Like, how long of a sequential thing is that? So first we need to figure out how much data is actually in a track. So let's look at the track capacity. So we're going to take the disk size, which is 2 to the 27, and we're going to divide it by the number of tracks, which is 2 to the 10. So we're going to get the track capacity is 2 to the 17. Okay. Now, we don't talk about sectors here. We're actually talking about blocks. And a block, for the record, as we're going to see when we talk about file systems, is a block is some sequential number of sectors. And in fact, when we do reads and writes to disk, we actually usually don't issue them in terms of sectors. We usually issue them in terms of blocks, just to minimize the seek time further. So how many blocks per track? So let's figure that out, because that's going to tell us what percentage of a full rotation do we need to make in order to read through this block. So blocks per track, we're going to take the size of the track, which is the track capacity, and we're going to divide it by our block size, which is 2 to the 12. And we end up with 2 to the 5, which of course is 32. And so that means that our transfer time is 1 over 32 times the cost of a full rotation. So we're going to say that this works out to be, so this is 1 over 32 times 10 milliseconds. We're going to say this is about 0.3 milliseconds. Now you can leave this in fractional form, that's fine. I'm putting it in decimal form because I'm lazy. That is so annoying. Oh, I love it. No, I don't. Okay, so So let's add up these costs to get our IO request service time. So IO request service time is average rotational latency, 5 milliseconds, plus average seek time, 5 milliseconds, plus the transfer time, which we've computed to be about 0.3 milliseconds, which gives us about 10.3 milliseconds is how long it takes to do one IO operation. Okay. Now that we have that, we can now go back in and actually compute our CPU utilization for this. So let's draw this out. We've got one process, and it's going to do 5 milliseconds of compute. After doing its 5 milliseconds of compute, it does its IO operation, which is going to cause it to block, of course. And we know that that is 10.3 milliseconds. And then it repeats. So this is compute, and then IO dot, dot, dot. Now, to figure out the CPU utilization, we need to find a repeating unit here. And if I look, I've got this compute IO cycle. So what is the length of this compute IO cycle? Well, it's 5 plus 10.3 milliseconds, or 15.3 milliseconds, not meters, obviously. So to compute our CPU utilization here, I see CPU utilization is equal to the amount of time we are computing divided by the total unit of time that we have, which is 15.3 milliseconds. So we're getting about 1/3 utilization. You can leave it approximate here. All right. Now, part 2 asks you to repeat this question, except instead of doing one process, let's do 2. So now that we actually know the IO service request time, we don't actually need to recompute that. But here's something that you do need to pay attention to. You can only do one IO request at a time. Those platters don't move independently. I can't do an IO request on this platter and an IO request on this platter in a different position at the same time. That we don't do that. So what we're going to end up with here is we've got P1 and P2. So P1 goes first because that's just the arbitrary choice that we make, and that's our compute. And while P1 is doing its compute, P2 is idle. And then P1 does its big IO operation. Now, because P1 is doing its IO operation, it's blocking, which means that P2 can now go. And it does its compute. Now, it can't, at the end of that, do its IO operation because the disk is already in use. So we're going to have to wait. And then what we're going to end up with is after the IO operation for P1 is completed, then we can do the IO operation for P2. And while P2 is doing its IO operation, P1, of course, can come and do its compute time. Pretty cool. And this would repeat, where the two processes go back and forth doing IO operations. Now, to compute the utilization here, we need a repeating block. We're going to ignore the head and tail, and we're going to look, and we see that the trend is for this to repeat. Now, while it alternates between P1 and P2 doing the IO operation, the pattern is the same. There's an IO operation and a compute cycle happening at the same time. So that is our repeating block we're going to use to estimate the CPU's utilization. So the length of the repeating block is 10.3 milliseconds, and the length of the compute is 5. So you're going to get about half. Not bad, right? So here's a challenging problem for you if you're really bored sitting at home, and I know it's nearing the end of the term. So if you're you don't have all these assignments due, you could see what happens when you have 3 processes and see if there is any number of processes that would give you 100% utilization. What is the best utilization you can get? So there's a challenging question for you if you're super, super bored. All right, so what I'd like to do now is to actually go back to the slides and continue our lovely discussion of our disk. So we've talked about how the disk works. We've talked about the fact that their I/O operations are actually quite expensive. But one of the things that we haven't talked about is how do we actually communicate with the hard drive. And we do that via the disk controller. Just a little bit of hardware, of course, that's on board the actual disk. And what we want to do is actually write our device driver and our handler for communications with the disk. So first, of course, we need our specifications for the device registers for our disk controller. So our disk controller in OS 161 is actually really simple because it's not even a real disk. But here you go. So we have for our disk this lovely little thing here, which is the number of sectors. So that is a status register, and the status register is telling us exactly how many how many sectors the disk has. And that can be used in the computation of, is this a valid sector that you're asking me to write to, or is it total garbage? So that's a very important one there. Then we have the status register, which is actually a status and command register. Now, how this works is if you read it, it's going to tell you if a read or write is in progress, and it's also going to tell you if it has completed or not. If you write to the status register, you will be writing either write or read to tell the disk, hey, I need to do a read or I need to do a write. Then we have the command register sector number, which you will write to this register to tell the disk which sector to read or write from. So you actually need to write to both of these registers to tell the disk what to do. Then we have a status register for rotational speed, which can be used in computations of how long is this going to take on average. And then we have a very large device register. It's actually 512 bytes in size. That is the transfer buffer where we will actually put data that we want to write to the disk or we will read from in order to get the data that we read from the disk. And the reason why it's 512 bytes in size is because remember that the disk, even if the operating system does other denominations for disks, the disk itself does sector-based addressing, not byte addressing, not bit-based addressing, sector-based addressing. And so when we do a read or write, we actually have to read or write the entire sector, and our disk has a sector size of 512 bytes, which is actually quite standard for the time. So let's look at the device drivers. So first off, we're not going to write a polling driver for this. We are going to write a driver that makes use of the interrupt because polling would be a form of busy waiting, and I would like my CPU to be utilized, but not doing something stupid like polling. So we're going to make use of the interrupts. So the first off, we note that you can only do one read or write on the disk at any time. You can't be reading 2 different things at the same time because you can't physically be in 2 different places at the same time. Now, I know if you're looking at some kind of quantum thing, everything is everywhere until you measure it, right? But we're going to pretend that that's not the case. So, because, well, I mean, after all, reading it is a form of measuring or looking at it. Sorry, random aside there. So we're going to need a way to protect the disk so that only one operation can happen at a time. So we want a lock. But we're not going to use a lock here. What we're going to do instead is we're actually going to use a semaphore, a binary semaphore. And we actually use binary semaphores in device drivers a lot, and there's very good reasons for that. And hopefully today you will see one of the very good reasons that we actually use a binary semaphore for this. So here you go. We're going to P the disk semaphore to make sure that we are the only person trying to read or write to the disk right now. Then to write to the disk, I'm going to copy the data I want to write to my disk into the transfer buffer. That's step 1. because it doesn't make sense to issue a command to the disk until the data is actually in its device register and ready to go. So we'll copy the data to the transfer buffer. And now, how does that actually happen? So interestingly enough, this could be a program-controlled I/O where the CPU actually actively performs the transfer, or this could actually be something like a DMA request where when we see that we need to copy this into the transfer buffer, the DMA controller takes over so that the CPU is not being idle or is not busy waiting here. Either way, you copy the data into the transfer buffer. The next thing you want to do is you want to write the target sector, so what sector should this data be written to, into the sector number register. And then the final thing to issue the final command to go and do it now is you write into the status register to tell the disk to write. Now, this is where things get interesting. You will see that we have a disk completion semaphore and that we P it. Now, I want to tell you that the initial value of the disk completion semaphore is 0, because what we are doing here is we need to wait for the disk to actually complete the task. Why do we need to wait for the disk to complete the task? Well, there's a few different reasons why we might want to wait for the disk to complete the task. If I am a user program and I am writing to a disk, probably my next operation may also be writing to the disk. And I don't want to write to the disk or continue on in my program until the initial write has actually completed. So I want the calling thread to block until the I/O operation has actually completed. This is one way to do that. Another reason why we might do this is once the operation has completed, I may need to retrieve, and we'll see this with the read handler, I may need to retrieve data from one of those registers, or I may need to check an error code. And it doesn't make sense for another thread to be checking an error code for me. So this disk completion semaphore is going to permit control to return to the calling thread. So the disk completion semaphore actually starts out with a 0, so that the calling thread gets blocked until the I/O operation completes. And this is actually one of the big reasons why we actually need to use semaphores, is that means that when the interrupt fires, the interrupt will not be handled to say that that I/O operation is completed. The interrupt will not be received by me, the caller, because I'm asleep. So another thread is going to handle the interrupt for the disk being done. That other thread, if we used a lock, doesn't own the lock and therefore wouldn't be able to wake me up. So you can see why we use a semaphore here. Because if we didn't use a semaphore, we wouldn't be able to wake anybody up, because you can only call lock release if you own the lock. And in this case, we actually need to release the semaphore, but we don't own the semaphore. So that is actually allowed with semaphores and not with locks, of course. So what we're going to do in the interrupt handler is we're going to acknowledge completion back to the device to say, good job, disk. I see that you have done. So we'll clear that out. Won't fire any more interrupts. And then we are going to V the disk completion semaphore to wake up the originating thread. And then in between the P and the V here in the original thread, once it's woke up and running again, we might handle any errors. And then we've noticed, okay, the operation is over. We're now going to release the semaphore on the disk and another I/O operation can complete. And the read handler looks very, very similar, except now we're actually going to do something between those two semaphores. So again, we P the disk semaphore to make sure we're the only I/O operation. Then we are going to write the target sector. We don't do anything with the transfer buffer yet because we are reading from the disk. So we indicate that we want to read, and then it is very important that we P the disk completion semaphore, because the originating program can't move on until we actually have the data. So we are actually going to we're going to cause this thread to block to wait for the I/O operation to complete. When the interrupt for completion is received by the handling thread, we will acknowledge completion once again, and we will V the completion semaphore, which will wake up the blocked thread that was waiting for I/O to complete. And then you'll notice that we do something when we wake up. We're going to copy the data from the device transfer buffer into memory, i.e. our address space. Now, technically speaking, I suppose you could have done this down in the handler, but that doesn't make a lot of sense because the thread that handles the interrupt for the device may not even belong to the same process as you. And how would one process be putting memory from a device into your address space? That doesn't make sense. We want you who asked for the data to put the data into your address space. So after we wake up the thread that called the operation, we will get it to get the data that was read out of the transfer buffer and copy it into its address space. And then we are finally done with the disk, and so we can view the disk semaphore. Now, a lot of people ask, do you need to have two semaphores in every device driver? And the answer is no. The reason why we needed two semaphores for this particular device driver is for two reasons. Number one, because the calling thread needs to block while we are waiting for the device, because we can't continue in the program until that operation has completed. The other reason why we need two semaphores here is because I want the thread that handles error codes or copying data into the address space to be the thread that made that request, because that's going to make it the easiest. So this particular device driver does need to have the two semaphore approach. That's what makes sense. But there are other device drivers that don't need the two semaphore approach. And if we go back in time in these slides, and we're looking at things like this is the console one. We didn't need a second semaphore here. And if you wanted to make, say, a device driver to cause the clock to beep, you don't need a second semaphore there, because the program that asks the clock to beep, you don't need to wait for the clock to beep. The clock beeping does not impact your program in any way, so we don't need the second semaphore for this particular device. Always depends on what you are doing. Okay. So that's kind of the end of discussing the mechanical hard drives. And what I want to do is move on now to the final topic, which is to talk about lovely solid-state drives. Now I feel like I want to fish around on my desk here. Oh, there's what I want. Fishing around on the upper layers of my desk for something. The question is, will I find it or will I cause everything to fall off my desk? So solid-state drives, these, as I've mentioned before, they are not a new concept. They've actually been around for a very long time, but it's only fairly recently that they've become feasible, cost-effective, and so on. For the average user. I know I got my first SSD, I want to say it was like 2008. And in 2008, I unfortunately bought one from a brand that was a decent brand, but they had, and I didn't know until afterwards, a failure rate of about 35%. And unfortunately, I had one of those 35% that failed. But nowadays, if you look at SSDs, their reliability has gone up. Now, why SSDs and what are they? So SSDs are very, very different from your mechanical hard drives. Your mechanical hard drives or your hard drives, whatever you want to call them, actually have glass in them. They have multiple motors because they have multiple moving components. The platters move and the read-write heads move. So there's lots of things to break and lots of motors to break down. If you look at an SSD, there's no moving parts. An SSD is boring on the inside. It's just a bunch of chips on a board. So we're using actual integrated circuits to store things instead of any kind of magnetic surface. So that's kind of cool. Now, I mean, some of the advantages, of course, are that you can fit a lot of memory in a really small space. So this here is it's a little micro SDXC card, and it's like the size of my fingernail, and this is 128 gigs. And it's about as thin as it's not much thinner than like a business card. Like it's tiny. Can you make something this small for 128 gigabytes with a mechanical drive? Of course not. That doesn't make sense. So one of the advantages of a solid state drive, aside from the fact that it has no physical moving parts, is that we can actually make them really, really small. I should probably put this in my Nintendo. Keep forgetting to do it. Oh well. I'll get to it. Okay. So what is inside those chips though? How do we actually implement that? Now, I'm no hardware engineer. I'm not a physics person. So you'll have to forgive me if I don't understand all of the great details, but a very high level overview. So there have been a few different implementations of SSDs over the years. One of the earlier methods was called DRAM. And essentially it was just your regular computer RAM, except it had a battery and some capacitors. So the idea was that in order for RAM to keep its value, it has to be constantly powered. So what they did was they put a bunch of capacitors, which you can think of as tiny little batteries. They can hold a charge for a small period of time, a small charge for a small period of time. And so they mixed these capacitors in with the RAM circuitry. And the idea was that there was also a battery on board so that when the DRAM was not powered externally, the battery was sufficient to periodically refresh the charge in the capacitors so that the RAM would actually keep its values. So DRAM did require constant power to keep its values, be it a battery or actually being plugged in. The question becomes, what happens if you need to replace the battery on your DRAM? So, yeah, that wouldn't be very good. But the method that actually won out is this flash memory. And we actually use NAND flash memory, which is made up of NAND gates. And it still requires like electrons in order to keep the charge, but how it does it is very different. There's no onboard battery. There's no like capacitors throughout. They are trapping electrons in a quantum cage. I don't know what that means. Again, not a hardware engineer, but it suffices to say that the technology is different. Now, does that mean that the values that you store on your flash drives will be there forever? Actually, no. My understanding is that after about 10 or 15 years, if that device has not been plugged in, then there's no guarantee that the data will still be there or not be corrupted. But flash memory is what we use. Another interesting story about flash memory. So if you go to like kind of computers on like some Black Friday deal, and you can always find like, here's like a 256 gig flash drive, $5. Now you have to ask yourself, if you look at any manufacturer of SSDs, you'll see they've got like, okay, here's my 4 gig one, here's my 8 gig one, here's my 16, my 32, my 64, my 128. They've got like all these different denominations. Do you honestly think that the manufacturer is making that many different denominations of hardware? The answer is no, they're not. So one of the dark secrets of the hardware world is, let's suppose you make 64 gig cards and you make 256 gig cards. Well, a 32 gig card is just a 64 gig card where half of the memory cells don't work. Or we've blocked in firmware the other 50%. Or we soldered an extra little piece here so that you can't access the other 32 gigs. So a lot of SSDs that you buy, even if it says 8 gigs on the packaging, it might actually have been a 16 gig one where only 8 gigs of the cells actually work. Dirty secret. And by the way, it's not just flash drives and SSDs that do this. This has also happened with CPUs and graphics cards. So there was a period of time where, and I heard this story from some people who actually did this, there were different levels of like Xeon processors, and for like $1,000 less, so there was $1,000 or a really big financial difference between the top of the line and the second one. And everybody bought the second one because if you were soldered this one pin, it turned it into the top of the line one. So the chips were actually the same, but due to a minor difference in like the soldering, that's how they got the two models. And so people will buy the cheaper one and put a little bit of solder on it, and they'd get the more expensive one for free, almost. And the same is true for things like graphics cards. They don't actually have like 500 separate models of graphics cards. They actually have a few models where they make just tiny changes to disable or enable certain features. Fun story. If you're into hardware hacking, I'm sure you can find lots of things on the internet about that. All right, so you've got your SSD, but it doesn't have any mechanical magnetic surfaces. So how's the data actually stored? Well, we're not going to worry about tracks and sectors, but what we are going to do is we're going to logically divide this effectively RAM into blocks and pages. So the smallest denomination on an SSD we use is the page size. And the page size is usually 2, 4, or 8 kilobytes, most commonly 4 kilobytes. Now, I know when you had SSDs back in the early 2000s, you could actually, when you installed an SSD, you could actually set the page size, and you always had to set it to 4 because that's what your OS used. So you were restricted there. I don't think you have to, I haven't had to set the page size on an SSD in like a long time. I think it was just my first SSD you had to do that on. And then what they're also going to do is they take a bunch of pages and they group them together logically into larger blocks. Block sizes are always changing. They can be as small as 32 kilobytes. They could be 4 megabytes. They can be bigger than 4 megabytes. It depends on the disk. Now, when we are doing reads and writes, when we did that on a mechanical drive, we did that as segment-based reads or writes. When we are doing reads and writes of a SSD, we're going to do them at a page level. But there's some tricks. So reads can happen at a page level, and writes can only sometimes happen at a page level. And the only time a page write can happen is if the page has never been written to. Now, here's an interesting thing about SSDs. SSDs, we think of empty or unused as being 0. But on an SSD, empty or unused is 1. And in order to transition from 1 to 0, it doesn't take much energy. There's not much voltage required to do that. So empty pages are 1. And if you are writing to an empty page, you can go ahead and do that. However, you are not permitted to overwrite a page that is not clean. And the reason is that in order to go from a 0 to a 1, you need to apply a much higher voltage. And the devices cannot do that high voltage application at a page level. They can usually only apply a high voltage to a larger area, so they can only do high voltage applications to a block. So you can write to a new page, but you cannot overwrite a page. You have to overwrite the entire block. Which leads us to some interesting algorithms for writing or overwriting and deleting things from flash memory. So the naive solution, which is easy to implement but very slow, in order to overwrite a block, what you've got to do is let's say, actually, we're not overwriting a block. We just want to overwrite a page. Well, we have to figure out what block that's a part of, because we can't overwrite a page. We have to overwrite the whole block. So we're going to read the whole block into memory. Now remember, this could be 4 megabytes. So instead of overwriting 4 kilobytes, now we're doing a 4 megabyte transfer or more. So we read the whole thing into memory. And then we are going to reinitialize that block on the SSD all back to 1s. We are then in memory, we are going to update our block so that the page we wanted to overwrite now has the correct values, and then we write the whole block back to the SSD. That's a lot of steps. We've got to read into RAM, reinitialize the disk, update in RAM, and then we've got to write it back to the disk. This could be 4 megs, this could be 32 megs. This is not cheap. I mean, on today's computers, it's not bad, but if you consider how many operations are happening, this could actually add up pretty quickly. So smarter SSD controllers have tricks to try to avoid the naive solution whenever possible. And the idea is that the SSD, I'm going to actually draw this out because it'll be more fun, right? have multimedia presentation. So what you've got on the SSD, you should really learn the shortcut for this, is the SSD controller has a kind of page table. And it's going to keep track, and this could be actually supported by the operating system as well, but it's going to keep track of all the pages and whether they are in use. Sorry, this is in use. Because remember, on an SSD, one is free. And what's going to happen is, let's say we want to overwrite page 0x4. And let's say this is 0x4. Okay. If I wanted to overwrite this page with the naive solution, I'd have to copy it into memory, clear it out, write it back. That's a lot of work. But what if I don't? What if instead the file was using this page, but what if I altered the file to say, you know what? I don't want to overwrite this right now. It's too expensive. So what I'm going to do is I'm going to ask the SSD controller for a free page. And it's going to be like, oh yeah, here's my free page right here. And then I'm going to write what I wanted to overwrite this page. I'm going to write it to this page instead. And then I'm going to modify the file so that it uses this page instead. So we're doing this little trick to avoid overwriting blocks by, instead of overwriting a page, we'll just find a new page and modify the file so that it uses that page instead. Now this doesn't work forever, obviously, because at some point you are going to run out of free pages. And so periodically you actually have to do garbage collection. I believe the operation is called trim, which wasn't originally supported by things like Windows when I got my first SSD. All right. So that's kind of fun, right? Little nifty algorithms that SSDs do to improve performance and reduce having to copy things into memory to do overrides. So you might be thinking to yourself now, SSDs sound so great. They're so fast. There's no moving parts. They have all of these tricks to avoid overwriting things. What's the downside of an SSD? Unfortunately, there is a downside. So one of the things that can happen is the SSD controller can die. And if the SSD controller dies, well, good luck getting your data off. A lot of the information used for these translation tables is stored as part of that SSD controller. And if the SSD controller gets fried, you often have no way now of actually finding your data on the disk. Or the disk will lose power, or there's a number of things. And this is actually what happened to my original SSD that I bought many, many years ago, was the SSD controller died. And I was not able to retrieve the data from the disk because I couldn't actually interact with the disk. Now, here's another interesting thing. The circuitry that's in an SSD, there is a limited number of times that you can actually write to each of those cells. Now you might be thinking, oh, it's millions or billions of times. This is not something I need to worry about. Wow. Hold on a moment. The cells in an SSD can typically only be written about 100,000 times before they won't work anymore. The idea, my understanding, is you can only apply, each time you apply the voltage, you may have to apply a little bit more. And there comes a point where you actually can't supply sufficient voltage to cause the bits to change. So, this causes some interesting other algorithms that have to be done on an SSD. One of the other SSD controller's jobs is to do something called wear leveling. The idea behind wear leveling is, instead of having certain blocks or pages of the disk wear out before others, so let's say you've got a disk and let's say the first 100 blocks. You don't want them to wear out prematurely when the rest of the disk is fine, because some SSD controllers, once they reach like 5% of the disk is no longer writable, they'll mark the whole disk as read-only, and then your whole disk is dead. So some cheaper controllers do things like this. Now, more expensive disk controllers from the better manufacturers, it's not to say they don't do this, it's just the threshold where they mark the whole disk as read-only is a lot higher. So in order to make sure the disk is all wearing down at roughly the same rate, they do this thing called wear leveling. And part of wear leveling is we actually want the data to be randomly scattered across the disk. And conveniently, because there's no moving parts, the difference in I/O read and write time for random versus sequential I/O is negligible. So that's okay. Now, this actually brings us to an interesting discussion of this defrag operation. And in order to do defrag, as I mentioned before, we don't actually store our file as one contiguous chunk, because then we end up with external fragmentation of the disk, like parts of the disk where we want to write a contiguous segment to, but we can't. So we divide the file and the disk up into blocks or pages, and we do kind of the page table thing. Now, ideally, we want the file's pages to all be consecutive, like all be beside each other to minimize seek time. But usually that doesn't happen, or over time it gets thrown around a lot. So you end up with a very fragmented disk, and not fragmentation that I don't have enough memory, fragmentation in the sense that my file is scattered across the disk. So what ends up happening is you run defrag to take all the pages of the file and put them sequential. Don't do it on an SSD, because if you do that, number one, you are prematurely wearing out the disk because you're doing a bunch of write cycles that have no benefit whatsoever to the disk. And furthermore, because the file now lives in one place of the disk, you're going to end up kind of breaking down that wear leveling, and you could prematurely wear down one part of the disk before others. So defrag can actually help kill SSDs, so don't do it. Very bad. Comment on Twitch was that someone said they had an SSD died, and it was the controller, and they were able to recover the data, but it was really, really expensive. Yes. So it's not like in the old days of SSDs, it wasn't possible, but nowadays it may be possible by replacing the controller and doing some other fancy stuff, but you are going to pay out the nose for it. And the last I tried, so back in probably, I want to say it was like 2007, I had a mechanical hard drive go down, and I was looking into actually paying to have just a regular hard drive's data recovered. That was $500. I can't even imagine what the cost for that is today, let alone to do that for an SSD. So it is not cheap, and it may not always work for SSDs. So SSDs, they have their advantages because there's no moving parts. They can handle larger temperature ranges, so they can handle lower temperatures, they can handle higher temperatures. They use less power, so they're great for battery-operated devices. They're smaller, and they're faster because, again, no moving parts, but they are not without faults. If the SSD controller dies, you may not be able to recover your data for a reasonable price or at all. If you also have this concept of the cells do wear out after a very fixed number of writes, which means that there will come a point where cells on your disk are read-only, or the whole disk becomes read-only, so it does wear down. And we also have this thing where you have to be careful about things like defrag. But as in general, SSDs are a great thing. Okay. One more kind of persistent storage that's kind of newer, and that is this idea of ReRAM, or resistive RAM. And the idea is this is RAM that can actually have its values persist in the absence of power. So without power, the RAM is going to keep its value. And there's ReRAM, as I said, but there's also 3D X-Point, which is also known as Intel Optane. Now, what is this stuff actually used for? So it's not used generally as general purpose RAM for your computer. It's not to say it can't be, and certainly there would be some advantages to that, although it is not quite as fast as RAM. So maybe we don't want to use the resistive RAM for this. What we actually see resistive RAM or Intel Optane used for is caching to improve the performance of secondary storage. So here's the thing. Let's suppose you're something like Amazon and you've got the Amazon database. As you can imagine, that's a lot of data. Amazon has so much crap on it. And it's data that's going to be used a lot, especially around the holiday times when people are during the pandemic, where the only way you can really safely shop is on the internet. So they've got this massive database that's stored on disks that people are using frequently. So that's going to be a lot of I/O operations. And think about all the service request times on these servers. So what they want to do is they wanted a way to cache frequently used parts of the database, frequently used blocks of data from the hard drives, so that they can overall start reducing the cost of reading from secondary storage. And that's what they use resistive RAM for, or Intel Optane. It's actually being used as a cache for secondary storage. So you're going to store file data blocks in the cache that's stored on this RAM. And it's not as fast as RAM, but it's faster than secondary storage, so you are actually improving time. So what happens is when you want to read or write, you first check the cache, and if it's in the cache, then hey, you don't have to go to secondary storage. And if it's not, then you go to secondary storage and you may or may not put it into the cache. So that's really fun. And you'll learn more about how you could actually take advantage of this kind of technology when we talk about file systems next week, because you'll see what kinds of data we are going to need from the disk for our actual files themselves. All right, so that's the end of devices, and hopefully that's been somewhat interesting. One last thing I will say about SSDs. So if you're like, how do I buy a good SSD and hope that it works? So here's my recommendation. Buy an SSD from a company that actually makes the NAND flash memory. So there's a lot of companies that don't make the flash memory themselves. So they actually purchase it from the manufacturer and then they repackage it as their own. Don't buy those ones. So generally speaking, you want to buy it from the people that make the flash memory themselves. So I have had really, really good luck with Crucial. And you may be thinking, oh, Crucial doesn't make their own memory. Actually, Crucial is a subsidiary of a company that does make it. So Crucial's a really good one. Samsung's discs are supposedly pretty good, and Intel is another great one. But if you've got some random Quantum Fireball SSD, don't buy that. Sorry. I'm laughing at something that is related to hard drives, but you probably don't know. So there used to actually be a lot of other hard drive manufacturers over the years. Quantum was one of them, and they had this disc series called the Fireballs. And I swear they were the worst discs ever. Had like the highest failure rate. So whenever you make fun of discs for failing, you call them the Quantum Fireballs. Of course, that was the 90s. All right, anyways, enough ranting. So we will see you next week, where we'll start talking about exciting lives of file systems.